This is some definitions, right? Beta is how fast you're going in terms of the speed of light, right? So if something is stationary, beta is 0. If something is going at the speed of light, or at least close to the speed of light, beta will begin approaching 1. What will happen to the gamma factor, right? When beta is 0, gamma is 1, right? Relativity factor. As beta approaches 1, what happens to gamma? As this gets closer and closer to 1, this starts reaching 0, gamma approaches infinity. Okay? So that's when we say in relativistic terms that you are going at relativistic speeds because your gamma is approaching infinity. Right? So if we make a plot of gamma versus beta, when beta is 0, gamma is 1. When beta approaches 1, the gamma factor starts getting bigger, bigger, bigger. The closer something is moving to the speed of light, the more relativistic speeds that they're going at, and the gamma factor starts approaching bigger, bigger, bigger numbers like infinity. Is equal to gamma 1 plus beta lambda source. Now, we also define something else now. In astronomy, this is known as the redshift factor. Redshift factor. This is known as Z. The Z is defined as this. It's the change of lambda over the lambda of the source. Okay? That's its definition, right? So what is it getting at? If something is stationary and it's not moving at all away from you or towards you, then it will experience no change of wavelength. So Z should be 0 if the beta is 0, right? If something experiences a big change of wavelength, the bigger and bigger and bigger this is, the bigger this should be, right? So as beta approaches 1, something should experience infinite shift, very, very huge shift. And so the Z should start approaching a huge, huge number, okay? What number is that? Well, we could actually calculate an expression for Z here. Z is equal to what? Delta lambda is the difference of the two, right? Lambda observer minus lambda source over lambda source. One plus beta lambda source minus lambda source over lambda source, right? And so lambda source, lambda source, lambda source cancel, so you have Z is equal to gamma multiplied plus gamma beta minus 1. Okay? So according to this equation, that's the redshift factor, right? So let's go back to see what's going to happen. If beta is 0, what's going to happen? Well, this is going to be 0. What's the gamma going to equal? Well, we had said here, as beta is 0, what's the gamma? When beta was 0, gamma was 1, right? So if beta is 0, that means gamma is 1. So if beta is 0, gamma is 1, 1 minus 1, Z is equal to 0. So that makes sense. No redshift is experienced, right? Okay, when beta approaches 1, gamma approaches what? We said gamma approaches, remember I drew the graph? When beta approaches 1, gamma approaches infinity. Infinity. So then this becomes what? Well, when beta approaches 1, this and this becomes, it acts like, almost like 2 gamma, right? So Z starts approaching 2 gamma minus 1, right? And of course, 1 is not going to make any difference, right? So Z starts approaching 2 gamma, right? And then gamma starts approaching infinity. So basically, as you go close to the speed of light, you experience a redshift amount equal to twice your relativistic factor gamma. if I want to write the z for non-relativistic speeds, so beta is almost equal to 0, right? So how would I write the z? Z would be equal to 1 over square root of 1 minus beta squared plus 1 over square root of 1 minus beta squared times beta minus 1. I would do a binomial expansion of this, minus beta, 1 minus beta squared to the minus half. And then I would expand this to the first power. You have 1 minus negative half beta squared. And then there should be a negative half here. And then plus beta 1 minus negative half times beta squared. Because the other terms are going to be so small that you could ignore them, right? And then you're going to have minus 1. So you're going to have what here? 1 plus beta squared over 2 plus beta plus beta cubed over 2 minus 1, right? And so therefore you're going to have 1 cancels 1, and z is going to equal beta plus beta squared over 2 plus beta cubed over 2, right? Beta is small, you could even ignore this. Beta squared is going to be a lot smaller than beta. Beta cubed is also going to be a lot smaller than beta, so you could even ignore that. So you can say if beta is small, so z is going to equal delta lambda over lambda, and that's equal to just beta approximately, which is v over c. So for objects that are going at non-relativistic speeds, if I want to know how fast they're going, I just do the change in the shift amount divided by the original, and then I can get how fast that they are going. So applying this to the previous problem, remember I did the problem where the shift amount was 656.85, and then the original Balmer line was 656.3. You divided that by 656.3, you get v over c, approximately. So you should end up getting the velocity of precession of the star close to the answer that we got when we did the relativistic actual equation, right? So this one gives us, we calculated 651.4 kilometers per second. So very similar to the answer that you get if you do the actual results. So for most objects that we know of that are receding away from us at non-relativistic speeds, then you can just simply do z as the ratio of v over c. Now, if you get to bigger and bigger values of beta, the z value changes, right? So it's no longer going to equal v over c. It's going to equal to the general equation, right? So what was the general equation for z? We could also express this in terms of just in terms of beta, or just in terms of gamma. We could say 1 over square root of 1 minus beta squared plus beta over square root of 1 minus beta squared minus 1. Or we could express it in terms of keep the gamma and then rewrite beta in terms of gamma, right? Gamma is equal to 1 over square root of 1 minus beta squared. 1 minus beta squared is equal to 1 over gamma squared. And then therefore beta squared is going to be equal to 1 minus 1 over gamma squared. So now you're going to have here gamma plus gamma, and then beta is going to equal square root of 1 minus 1 over gamma squared. Right? And then z is going to equal gamma plus, you could bring the gamma squared into the inside. You're going to have gamma squared minus 1 minus 1. So the general equation for z can be written as either 1 over square root 1 minus beta squared plus beta over square root 1 minus beta squared minus 1, or gamma plus square root gamma squared minus 1 minus 1, or you could express it as gamma plus gamma beta minus 1, either way. So, in terms of realistic examples, now we've discovered objects in the universe with redshift factor z in the order of magnitude of z equals 3, 4, 5, 6. These are called extreme redshifts.